Okay, so good afternoon, everyone. Welcome to the N3AS room seminar. We are very glad to have Dr. Ting Li to be our today's speaker. Ting is now the NASA Einstein Fellow at the Carnegie Observatories and joined Carnegie Princeton Fellow at Princeton University. And she will join the Department of Astronomy and Astrophysics at the University of Toronto as an assistant professor this summer. So today, Ting will tell us something about the Southern Stellar Stream Spectroscopic Survey. Ting, please take it away.
Thanks very much for the introduction, and thanks so much for inviting me to give a seminar here. So I'm mostly an astronomer, observational astronomer in near field cosmology, or say like study stars and galaxies in the Milky Way. So I think most of the people in the audience are more fundamental physics related and like interested in like particle physics and nuclear physics, etc. So I try to make the talk a little bit oriented to more dark matter oriented than observational, although I'm doing a lot of science like related to dark matter stuff, but more focusing on observation. So today I'm gonna introduce you a new survey that I'm leading since about 3 years ago. It's called the Southern Stellar Stream Spectroscopic Survey, or S5. Because it's too long and it's all S, so I'm gonna just shorten as S5 later on. So I'll start with what a stellar stream is. So what you're seeing here is like a Milky Way-like halo, and here are a lot of either you can consider as star particles or dark matter particles, but the idea is if there's a group of stars either in a dwarf galaxy or in a globular cluster in the Milky Way halo, when it's orbiting the Milky Way, if it gets close to the Milky Way center, then it gets tidally disrupted and form this kind of linear long structure on the sky. And what we see is going to be these kind of linear overdensities, and that's what we call stellar streams. So these stellar streams are either disrupted dwarf galaxies or globular clusters. So these kind of things are actually being observed observationally. So I have been working a lot in a survey called the Dark Energy Survey. So it's an imaging survey in optical using a telescope in the southern hemisphere in Chile. And so this is roughly the footprint of the Dark Energy Survey. And what you are seeing here is the stellar density counts scanning through distance between 6 kiloparsec to about 60 kiloparsec. This is a work led by Nora Ship, who is going to graduate actually next week. Well, who is going to defend her thesis work next week, including this part of the work at University of Chicago. So what you are seeing here as we go through the distance, you will see some, so the dark means, the black means over density, the white means lower density. So you can see these kind of linear over density come, right, and goes. So these are the stellar streams we actually discovered from these optical imaging surveys. But we just simply counting the stars at each distance being, and then we see these kind of linear structures come at a particular distance and disappear at a further distance. So this stellar stream has been visible through a lot of these imaging surveys. And in total, the Dark Energy Survey discovered 13 new stellar streams plus 2 previous known. So in this footprint, at least we claim that we identified a total of 15 streams in DES. Okay, so I compiled a lot of data until I think 2018. There are a lot of things since then, but I've been lazy at kind of collecting them. So this is pretty much before the S5 start, the number of the stellar stream that we know, the cumulative number of stellar stream known as a function of the year it's discovered. So none of the stream are known before 1990s. You probably have heard of some of these famous ones. The first stellar stream discovered is called the Sagittarius stream, which is the disrupted tails of the dwarf galaxy, Sagittarius dwarf galaxy. So this is the first dwarf galaxy stream ever discovered. A few years later, using the Sloan Digital Sky Survey, a paper published to announce discovery of tidal tails around Palma 5 globular cluster. So this is the first globular cluster stream discovered. And since then, there's a bunch of other streams, some called GD1 stream, named after people who discovered it, or like orphan stream because there's no progenitor. And there's really like several dozens of stellar streams discovered using different imaging survey or satellite galaxies, satellite survey like Gaia. So there are Gaia surveys and like DES I mentioned earlier, and the Sloan and also like pan-star survey, etc. So there's over like 50 or 60 stream has been discovered by the end of 2018. And now I think there's probably almost over 100 stellar stream discovered. So why stellar stream are interesting? So I'm gonna give a little bit background on why we think it's interesting from the dark matter point of view. There are other, like in terms of like a galaxy assembly or like formation of galaxy, Milky Way, galaxy or Milky Way stellar halo. But here I'm gonna focus on the dark matter property. So a very important thing to understand a dark matter model, like distinguish between warm dark matter, cold dark matter, and self-interacting dark matter, is to measure the dark matter subhalo mass function. So here is an example of how the dark matter subhalo mass function looks like, right? So the cumulative number of subhalos as a function of the halo stellar mass. So the warm dark matter warm dark matter model predicts a much lower subhalo mass function, or fewer subhalos in Milky Way's compared to the Milky Way's host halo compared to the CDM and the SIDM. So it is important for us to measure the subhalo mass function to understand the dark matter properties and to differentiate between warm dark matter and cold dark matter. And another important thing that determines dark matter subhalo mass function is the mass of the host halo. The more massive the galaxy is, then the more subhalo it has. And here is illustration of plot from the dark matter simulation showing like the abundance of the subhalo in CDM, SIDM, and WDM. So the warm dark matter have much fewer subhalos compared to the CDM. So the first thing we wanted to study is what is the mass of the host halo. So Milky Way is the galaxy we reside in. It is the mass at about 20 kiloparsec or below is pretty well constrained. So this is the work showing that the Milky Way mass profile, so the mass within a distance as a function of the distance. So at about 20 kiloparsec, you can see different measurements give very consistent result. But beyond, I would say 50 kiloparsec, the measurement on the Milky Way mass can easily differ by a factor 2 or more. And most of these measurements are from either point tracers like globular clusters or dwarf galaxies, or using a single stellar stream. So far, no one has really combined all the streams together, like although we have like almost 70 of them, no one has combined all of them together to constrain the mass of the Milky Way. And this is a prediction made by Bonazza et al. In 2018. So the idea is showing like the halo scale velocity, halo scale radius as a function of number of streams used. So with one stream, some of the uncertainties can be 10% to 100%, but as combining more than one stream or over 10 stream, then the uncertainty uncertainty on the halo mass and also halo potential profile, like the flattening and also the scale radius, can be dramatically improved. So the idea is that we can use a dozen or 2 dozens of stellar streams to constrain the Milky Way mass globally. So this is one part for the dark matter subhalo mass function. We want to know the mass of the Milky Way more precisely in order to know what is the predicted number of dark matter subhalo in a warm dark matter model and in a cold dark matter model, for example. The other thing is here, what you are seeing have like dozens to thousands of subhalo, but this subhalo doesn't necessarily all forming stars and forming galaxies. So we know like Milky Way has dwarf galaxies, satellite dwarf galaxies surrounding in the Milky Way. However, these are all the dark matter subhalos with halo mass more than probably 10 to the 8 to 10 to the 9, that the galaxies are the subhalo are massive enough that they can retain enough gas to trigger star formation. However, below 10 to the 8 or even 10 to the 7, the dark matter subhalo cannot really form stars. So these are really true, like say, dark galaxies that we won't be able to see them by observing galaxies. So the other way we think that we'll be able to measure the subhalo mass function down to 10 to the 8 or 10 to the 7 is through measuring the gaps in the code stream. So what you're seeing here is two streams, one on the top and one on the bottom. The only difference is on the bottom, it was putting in some and a CDM model with subhalo perturbation. So in this particular video, you'll see two subhalo passing by. So this one, I think, is around 10 to the 7, another is around 10 to the 5 to 10 to the 6. And the idea is that when these subhalo passing by, pure due to the gravitational impact, the stars in these stellar streams move around and forming this density variation in the stream. And so based on the property of the stream that measured, we think that we can like recover or say measure or derive the perturber or the flyby subhalos property. So here is the example. So this work is on GD1 stream. I saw a question. Do you want to, I saw a hand raised. Do you want to ask a question?
I think, yeah, Yanis, if you want, yeah, you can just ask your question now.
Yes, thank you. In the previous video you showed us, this is a compilation of frames, right? And I was asking what's the time between each frame when you compile that video.
Is that the question you're asking?
Yes.
So this one is about 2 gig a year. You see the time scale here? So the whole video is about 2 gig a year.
2 gigayears, okay. Yeah. And how many frames are in that video, do you know?
How many what?
Frames are in this video.
No, it's made by Dennis Alker, but I believe he was doing a digital 0.01 gig a year. So it's total of 200 frames.
200
this
frames.
Is, yeah, but this is just illustration. I won't say like it definitely a stream will have two perturbation, like two flyby in a year, in the course of 2 years. I think depend on the orbit of the stream, how far it is to the Milky Way center, etc. So this is just illustration, give you idea that if there are dark matter subhalo flyby, then we expect to see this kind of density variation through the gravitational interaction between the subhalo and the stream.
Okay, thank you.
Yeah. So this is the example of from a stream called a GD1 stream. So as soon as Gaia had the second data release, so Gaia DR2, NASA and her collaborator find that based on some simple selection, you see that the GD1 stream has a spur and a gap here. So that's what they call the gap and spur. So this actually was seen earlier using the Sloan data, but was not as obvious as what see from the Gaia data, because Gaia is able to remove all the foreground stars or majority of the foreground stars to minimize the contamination. So then using these top panel, which is from the data, so Gaia data plus Pan-STAR data. Then Anna Bonata did a model to show that with a perturber of about 5 times 10 to the 6 solar mass, and with a scale radius about 10 parsec, and with some other property of the perturber, you can kind of mimic what is seen here. Like, so this is a pure model using some modeling using the model of the perturber. So this kind of spur and gap feature can be produced with this model, and taking the scale radius and the mass. This is what they thought about the range of the perturber. So the perturber is likely to be in this area in the mass and the size plane. However, very interestingly, if you count all the dwarf galaxies, so these triangles, the squares, and also from the model, this shaded region, that's what we expect the lambda CDM subhalo would be lie on. So this is saying if this gap and spur is caused by subhalo, then the subhalo is more compact than what the standard lambda CDM predicts. However, I also want to point out that there's another work led by Du Bois et al., they show that the spur feature can also cause by an interaction between the stream with the Sagittarius dwarf galaxy. So that's something I also will mention later. But anyway, this just gives you one example of how the stream density variation have seen on the from the observational data and what we can use to do the modeling. But the idea is we have dozens of these kind of stellar stream. So we should really try to study these kind of features in the stream, not only just on one, but on a few dozen of these. And then based on the statistical answer, we should be able to rule out CDM is the right model, or if we should kind of go to the warm dark matter, because based on the subhalo mass function at say 10 to the 5 or 10 to the 6 solar mass. Okay, so this is why we think that the stellar streams are interesting from the dark matter point of view. And I'll go through things quickly because I've spent a lot of time on this. So I want to just emphasize that spectroscopy follow-up observations are very important because we find so many streams, but we also need to confirm these are real structures rather than just like artifact from the imaging survey. And also the spectroscopy follow-up will provide kinematics and chemical information for these stellar streams for us to characterize the stream progenitor. And also it will help us to identify these perturbation signature that I mentioned earlier. So I worked a lot on Milky Way satellite galaxies in the past. And there are also about 60 satellite galaxies in the Milky Way has been discovered at the end of 2018. But more than 70% of them have had observation spectroscopically. In contrast, the stream only have about 10% of follow-up. So here in the plot I showed earlier, a lot of them are discovered but lack of spectroscope follow-up. So in 2018, I started this S5 survey using a high multiplicity wide field of view spectrograph on a 4-meter telescope. So this is the AET, the Angular Australian Telescope at Siding Spring Observatory. The unique ability is that it has a 2-degree field fiber position with 400 fiber and feed it to a spectrograph. That means that we can observe 400 targets over a 2-degree diameter field at once. So that kind of largely increase the efficiency of our observation. So I started S5 in 2018. I talked to a few colleagues in Australia, and then we started this collaboration between the Dark Energy Survey Milky Way Working Group, which I'm chairing, and also a group of astronomers in Australia who have access to the AET telescope. Okay, so this is what we observed at the end of 2018. So this is the DES footprint I showed earlier, and here are showing all the stellar streams, where the stellar stream we found in S5 in DES. And so we observed a total of 10 stellar streams by the end of 2018. So first thing we did is we plot the velocity of high probable members as a function of right ascension and declination. So these are the first 7 streams that we observed in 2018. And after we plot these, we immediately see that these kind of stars, so if it's pure halo stars, then we would expect the dispersion, velocity dispersion to be something like around 100 to 200, which is the dispersion of the Milky Way halo. So we do see some kind of these stars here, right? Like also here. But more importantly, for a group of stars, for each stream, so each column represent a particular stream field. You can see the very tight velocity behavior here. So velocity dispersion is so small, and we confirm that each of these is a true stream, and we identify these stream members. But the more interestingly, in this plot, we find the 2 streams are super exciting, which is the Elika-Uma stream showing in brown here, and the Atlas stream showing in blue here. So these 2 are 2 separate streams under discovery, but when we plot them in velocity, we find that these 2 streams are seamlessly connected. So you can see the velocity for Elika-Uma kind of continues, follows with Atlas. So let me show you where are these 2 streams. So this is the Atlas stream, okay? And the Elika-Uma stream maybe not very visible here, it's here. So in this plot, it shows much stronger because it's at a further distance distant module about 17.6. And in this one, it's a little bit closer at distant module 16.7. So basically the Alec-Umar is slightly further away from Atlas. And also from the stream, you can see, although they are close on the sky, right? You can see there is a very obvious discontinuity between this stream and the Alec-Umar stream and Atlas stream. So when we discovered these two streams in the dark energy survey, we think these two are separate streams. One, because their discontinuity on the sky. Second, because the Alec-Umar stream is much further away compared to the Atlas stream. Okay, the next plot I'm showing is just rotating these things 30 degrees. So everything is on the stream coordinates. So this is the Alec-Umar stream, and this is the Atlas stream. And the Alec-Umar stream is much lower surface brightness compared to Atlas stream. And so here I highlighted the member stars we identified using S5 in the red circles. And then we plot all these stars in velocity space, in proper motion space, and also in distance space. So here you are seeing all the stars on the sky. So phi 1, phi 2, just along the stream and perpendicular to the stream. And then we also plot the star in velocity space, in proper motion space, and in distance. So you see that actually, despite this discontinuity on the sky, we do see that the velocity and in proper motion and in distance, all these member stars of the two streams seamlessly connected. So Atlas and Alec-Umar stream are actually one stellar stream, but has some discontinuity morphology on the sky. So now we have the proper motion and the distance information. We go back to do a similar selection as what the GD1 stream that did by Anna Banata's work I showed earlier. But to note that GD1 is around only 8 to 10 kiloparsec from us, while Atlas Alec-Umar is about 30 kiloparsec from us. So it's much farther away, which makes this much harder to do because they can select main sequence stars, which are more abundant, while here we can only select the giants. So here we select all probable member stars that basically fall in the velocity proper motion track and the distance track. And I also want to highlight the distance, we do see a distance gradient. So the Alec-Umar part, this part is much distant compared to the Atlas stream part, but it's kind of still continuous rather than a sudden jump. It just shows a distance gradient in the stream. Okay, with the selection in proper motion in the distance, then we're able to select all the stars here that we think are likely to be members. On the right panel, the gray area show the S5 coverage and the member stars identified spectroscopically. So now let's look at this plot on the left. I would say that this kind of feature here, we think most of these stars are probably member stars of this stream. And here there's also a broadening, that's what we call broadening feature, so cause a lower surface brightness in this area. So this kind of spur and gap feature is very similar to the GD1 stream, that spur and gap feature that's seen. However, again, Alec-Umar and Atlas stream is 3 times farther away compared to the GD1 stream. So we think that the baryonic impact is much smaller, but we still want to study that. First of all, what can cause this kind of density variation or discontinuity? First thing we wanted to study is whether or not like baryons, so not dark matter, but baryons like Milky Way bar, giant molecular cloud, the spiral arm of the Milky Way, classical satellite galaxies, or globular clusters, or the progenitor of the stream itself can, sorry, let me just stop, close my slide. Apologize for that. Yeah, if any of these can cause this broken stream or the discontinuity. So we studied each individual case and rule out all of the other ones except for the classical satellite galaxy. So we found that about 5% of the realization. So we basically take the classical dwarf galaxy's current location and use the current 6 information to rewind the orbit and see if it had a chance to interact with Atlas and Alec-Umar stream. So about 5% of the realization show that the Sagittarius dwarf galaxy can mimic such kind of a kink or say a spur feature that we see. However, it predicts a very different velocity behavior as what we see. We see a spread here, while the model shows that there should be an offset in velocity between. So the model here is the blue small dots, and the black and the yellow, red one with arrow bars are from the data. So you can see the mismatch between the model and the data. So we would say that the Sagittarius dwarf is possible with based on the current location of Sagittarius dwarf, there is and the uncertainty from the dwarf's information, there is about 5% of chance it can create such kind of feature. However, it's more likely that the dark matter subhalo would be the solution for these. And right now we are working on that to see what is the orbit and the property of this dark matter subhalo to causing such a broken stream feature. Okay, so I don't have much time to go through all of the details, but I just want to show you the example that we use S5 data to study this interesting Alec-Uma and Alice stream. And we are not only working on like kinematic property or dynamical property of the stream, we also use them to study the abundance and the metallicities. So this is another example on another stream called a Phoenix stream. So we measure the metallicities of each individual stars in the stream, and we found the metallicity of this stream is likely to be a minus 2.7 globular cluster. While we plot all the globular clusters in the Milky Way, we find none of the Milky Way globular cluster is above minus 2.5, which is what we call a metallicity floor in the Milky Way's globular cluster. So it is very interesting that we find a stream that whose progenitor is a globular cluster that more metal poor than any of the known Milky Way's globular clusters. But this is another example to show how we can use S5 data to study the chemistry and metallicity evolution of these globular clusters. And at the end, I wanted to highlight that S5 is not just a stream survey. So what I was talking about earlier is mostly focusing on the stellar streams. And I showed two examples, one from the kinematic point of view, another from metallicity point of view. But we also observe S5 in other three aspects. One is called S5 high res, in which we study the member stars and bright metal poor stars with high spectral resolution to understand the chemical evolution. And we also have a halo component, uses all the sphere fibers from the stream survey and then to study the Milky Way halo. And then we have another low Z program to study the low redshift galaxies that within redshift 0.02 to 0.05 to study LMC mass like galaxies in the local universe, again using sphere fiber from the stream program. So I don't have time to go through the detail, but I'm happy to answer your questions if you are interested in any of these results. Here I'm just going to illustrate one result from each program. So for the high res program, we find the first highly rapid neutron capture process enhanced star in a disrupted dwarf galaxy. So these stars in the stream show a much higher R-process enhancement than any of the other stars. So that's very interesting. And in the S5 Halo program, we find the fastest sequence star with a velocity of more than 1,700 kilometers per second ejected from the galaxy center. So this is I would say, the most exciting hypervelocity star that I ever find. And in the LOSI program, we have observed over 5,000 galaxies, and we find at least 100 galaxies with redshift below 0.02. So these are the stars at mass about LO1 to LMC mass. LO1 to 4 next to LMC mass. So this sample is also very interesting for us to study the subhalo mass function, the satellite luminosity function or subhalo mass function for different dark matter models. Okay, so if I will say all the things I've shown so far is based on our 2018 observations, then I want to say that S5 is expanding and we are observing beyond the DES footprint at the end of 2019. And we just had our first public data release last month via Zenodo to release all the data we observed in 2018 to 2019. And now we just had the internal DR2 data release for all the data taken up to 2020. So we have over 20 streams observed over 5,000 square degree. So I think this is very, very valuable data to do all the science related to dark matter, Milky Way archaeology, and other interesting science. So, okay, I think I'm already go over the time and I'll stop here and take questions. Thank you.
Okay, thank you for the interesting talk about the S5. So are there any questions for Ting today? Okay, I see George has the hands up. George?
Hi, thank you, Ting. That was a very, very nice talk. I really like that. Just a question about one of the last things you talked about, which is this very low metallicity R process enhanced star in these streams. I'm just wondering, how much is it enhanced? Does this look like the R process enhanced low metallicity halo stars that we all know and love? Or is it somewhat different?
So this plot that it shows all the, I would say, so we know that the halo stars are mildly in process, so which we call R1 stars. So most of the halo stars and global cluster stars are mildly enhanced at about something around between, it's not just a flat plot, but it's in this area. Okay, so and most of the dwarf galaxy stars are not enhanced, so it's in this area.
I'm just thinking the results that Frabl's group gets.
Right, so that's what I'm going to say next. So this is
Okay,
the
good.
Rectangular 2, which is from Alex G, and actually this work is also led by Alex because I asked him to join the group to lead the high-res part. So these 5 stars are from the Rectangular 2, the very famous dwarf galaxy, ultra-faint dwarf galaxy. So you can see that index is almost similar in terms of European to iron abundance compared to the rectangular. Rectangular is just more metal pool compared to the other one. And there are also a few stars that we know that have this kind of high enhancement in like Fornax and in Ursa Major. But I would say this kind of is like a empty region, because it's not classical dwarf, it's not the very low mass ultra-faint dwarf, it's kind of in between. So this is a star we find, and it's very similar in terms of the European abundance, it's very similar to the Rectangular 2 ultra-faint dwarf galaxy. If that answers your question.
Yes, thank you. But do you also see heavier elements there? Can you see, I mean, so for example, in some of these old halo stars, you can see uranium. So do you have enough photons and enough dispersion to see the really heavy things?
I think so in this, the follow-up paper, Hansen and all, we did study a bunch of elements. I'm not sure like what are particular there, but we did the data, because these streams are much closer compared to all of the dwarf galaxy because they disrupted. So we actually can get pretty high signal to noise ratio for the spectra. So we were able to measure like over 30 element abundance in this stream. So most of the elements, if they are available in optical, I think we have we were able to measure them.
So Cowan, for example, could actually use the uranium and thorium ratios in these old halo stars to get an age estimate.
Yeah, that's something we are thinking about as well. I think we haven't done that yet, but definitely it's going to be interesting to see if we can get some age constraint on all of these stars, not only just this particular one, but also all of the high-res data that we have collected. I just want to mention, I didn't say this earlier, but this is just one example, but we observed over 7 stellar streams with high resolution follow-up. And I think we have a total of over 50 stars already and published. And we have another 15 we are currently working on the next publication. But yeah, I think it would be very interesting to see if we can get some age constraint using the high-res data. We haven't done that yet, but that's a good suggestion.
Thanks, Ting. That's great.
Okay, so Gail has a question. Gail, please go ahead.
Yep. So thanks very much for a really interesting talk. My question is a follow-up on George's question. I'm wondering if we should read meaning into the fact that there's only one of these R process stars, or if it's observational and you expect to find, like, can we do some statistics yet with some stars that have europium and some stars that have less europium, or should we just wait for more observations?
Yeah, that's a very interesting question. So for example, the rectangular 2, right? I think among all of the one has high res, only one is not enhanced. While for Indus, among all the 7 we observed, so this cross here, only one is enhanced. So we discussed in the paper, in this follow-up paper, whether means it's an external process, or meaning like this happened at a later time when the gas get polluted. So we discussed some of this. I definitely think that we actually put in a VLT proposal to observe another about 7 or to 10 of the Indus member stars to double the sample, and want to see if we will find more. I would say if after like say 20 stars, only one come out of 20 is the only enhanced one, then that probably will tell us more about this star is more external kind of created or something like that. But I think right now with only 7 of them, we cannot make some conclusive conclusion yet. But we are definitely getting more of these bright members to see. The advantage in this stellar stream is because they are all disrupted, so they are usually closer compared to these intact dwarf galaxies. So we are able to get a lot of bright member stars for detailed abundance study.
Great, thank you.
Okay, Susan, so could you go ahead with your question?
Oh, yes, I have a great talk. Thank you very much, Ting. I had 2 brief questions in regards to the stellar stream study you presented. In particular, you mentioned that in your own particular S5 study, you were not concluded whether or not visible Milky Way satellite galaxies could potentially cause the break in the stream you saw. What I was hoping from you is a perspective on some of the other results that have been claimed in literature. So for example, there's this Bannock and Bovey and collaborator discussion or papers claiming that a joint study of GD1 and PAL5 they did claim there's evidence for perturbations that are due to dark matter and not other visible matter, but they don't mention the Sagittarius dwarf impact in their abstract. Are there reasons to believe that the geometries of those streams are such that we don't worry about the Sag dwarf in that context, or are they simply not neglected a very important effect?
Yeah, so the paper that they discuss is essentially the Milky Way bar, mostly the paper is talking about giant molecular cloud and say the Milky Way spiral arm. Can these kind of baryonic systems cause a perturbation on the stream and make these kind of density variation? So that's the paper talk about, and the conclusion is the GD1 stream, for example, and also the PAL5 stream, the density variation is not caused by giant molecular cloud or from the spiral arm or from the Milky Way spar. I think that's the conclusion of the paper, but that paper did not discuss the impact from the classical satellite galaxy, like what you said. The problem with this one, the problem with this one is the current location, especially the distance to the Sagittarius stream, is loosely constrained. Depending on what distance you use, you might give an impact on, for example, GD1 and this Atlas stream. I think for PAL5, there's never a chance that the Sagittarius dwarf will impact on PAL5. But based on this work and also the Thomas de Broy's work I mentioned earlier, if you accept a certain distance with certain uncertainty distribution for Sagittarius, then there is a small chance, like 5% out of like say 100 out of 5,000 realization, we modeled that the Sagittarius dwarf might get close enough to the stream that make this kind of kink. But again, if you adopt other distance information for Sagittarius dwarf galaxy, or you make the uncertainty small enough, then you will have 0% of the chance that to cause this. I think this is really, we currently also working on say, if this is caused by Sagittarius, then what is the true distance to Sagittarius? That's kind of another way of study we are doing. But my point is people has been considering classical satellite galaxy before and rule out most of the case based on the classical dwarf's current location. But the uncertainty on this measurement, on the 6D measurement of this classical satellite galaxy are so large that I don't think anyone has a conclusive conclusion saying that any of the kink or gaps or perturbation signature we saw coming from any of the satellite galaxy. But I think this is the part that need more study, especially now we show that there is a possibility that Sagittarius can cause this, despite there is still a mismatch in the velocity. And also there's another work show that GD1's kink the spur may caused by Sagittarius. I think there need to be more work done on this. But the first thing is we need to have better constraints on the dwarf galaxy's current location. I hope I answered the question.
That's actually extremely helpful. Thank you very much. And then just a super fast question about the Phoenix stream, which you said was extremely metal poor. We all know that from Gaia, they discovered this Gaia Enceladus galaxy, which is metal poor and had anomalous kinematics. And I guess what I'm wondering is the Phoenix stream, is that also an anomaly? Could that have been generated or been associated with an ancient impact as well?
Yeah, that's a very good question. So first I want to say, this is not, I think one thing is though we see a lot of globular clusters in our Milky Way, right? And a lot of these Milky Way globular clusters are within say 5 kiloparsec or even within 3 kiloparsec. They are mostly metal rich and they are very compact and they can survive under the Milky Way's potential. While these, like Phoenix stream, the pericenter of the Phoenix stream never get within, I think, 10 kiloparsec. So it never get within 10 kiloparsec. If it's a Milky Way, like a Milky Way globular cluster, how could it get tidal disrupted? So we in this paper we discussed, it's very likely like the Phoenix stream is a globular cluster of another dwarf galaxy and then fall into the Milky Way's potential. And its host galaxy, like maybe its host gas is like in this stream, like progenitor, but another dwarf, maybe another example is maybe like its progenitor is maybe something like, what is it, like Carina or Sexton dwarf galaxy. But then that dwarf galaxy get tidally disrupted first. And then these dwarf globular cluster also get disrupted at the later time. So this is what we think the progenitor of these globular cluster streams. They are not the globular cluster from Milky Way originally, because all these Milky Way's globular clusters, they are more compact. They can survive under the tidal force in the Milky Way. But these ones, they originally get shielded under the dwarf galaxy of their host halo. But then when their host halo get disrupted, these ones formed in a much lower mass dwarf galaxy, so they are much puffier. And that's why they got more easily tidal disrupted. That's what we think. So yes, this would be very simple. So and Gaia Enceladus is another example, I should say. But from the orbit, we know it's not a Gaia Enceladus globular cluster. It's a globular cluster of something else that we cannot identify, at least now. But there are other work like the H3 survey, like talking about other substructures we are seeing more than just Gaia Enceladus. So this could be a globular cluster of one of the other dwarf galaxies that fall into the Milky Way in the past. But yes, all of these globular clusters from these streams, they are not the Milky Way globular cluster originally. That's also very interesting, right? The metallicity is much lower than any of those Milky Way ones.
Great, thank you very much.
Kim has a question. Kim?
Yes, thank you. That was a very great talk. Thank you. I just had a question about how long you thought it would be before you would start to actually measure the mass function of the subhalos and start to be able to tell, is this cold dark matter, warm dark matter? When do you expect that kind of analysis to be coming out?
I think this is going to be a long time to do this, but definitely that's something we aim to do, like during the era of LSST. I think the first step is we confirm a list of real streams and especially cold streams. So we wanted to use like the stream that whose progenitor is either low mass galaxy or globular cluster, because like Sagittarius stream, it's very abundant, but the velocity dispersion is also too big that it won't be able to use for this kind of study. But I think the first step is to find like a dozen of these kind of streams, and then identify these density variations. So people have already started doing this. As Susan mentioned earlier, people have used the GD1 and Pile 5. These are the only two streams people have used to do this kind of study. And I think we need probably at least like 10 of these kind of streams to do a more rigorous study. And I would say, at least say with 10 streams, we can, if we don't see enough gaps and like spurs all these features in like 10 stream below like the lambda CDM prediction, then we can rule out lambda CDM at certain like percent, like 2 sigma or 1 sigma percentage. Yeah,
so thank you. That's exactly what I wanted to know, and that's
right. But if I want to, another I want to say is, if we find enough like this kind of signature, we still cannot say we confirm the lambda CDM, because I think we need to carefully study all of these features to rule out it. So I think we need to have like at least 10 of them, and I'm sure that the next generation, like in the LSST era, we will get that sample size, and then we can do this kind of study. But it need to be super careful. If we a lack of this kind of perturbation signature, then we can rule out lambda CDM. If we do see this signature, we still need to rule out these to confirm lambda CDM, is what I would say.
Makes sense. Thank you.
Okay, so Ducky has a question.
Yeah, hi. Thanks for the nice talk, and I think you probably answered part of my question already. So I'm wondering, since you mentioned that considering satellite dwarf galaxies can explain some of the density kinks in the stream, but the velocity profile that does not match. So do we understand what's causing this mismatch from satellite?
This part?
Yeah.
So what all we did is we take the current satellite the location of the Sagittarius dwarf, right, and then rewind it back for like 2 gig a year, and then let it move and let the stream also move, and then run it, and then we get to the end position of the stream model to be those blue small dots. So and the velocity to be something like that. So it's a pure like embodied simulation on this, controlled simulation on this. And as I mentioned, this is only 5% out of all the realization we run, and it changed dramatically depending on what the initial parameter we used for the Sagittarius. So I would say this is just saying it's not saying why it's not mismatched. It's really that's the outcome of the simulation, and we see this mismatch. So we are saying the Sagittarius cannot explain the kink we are seeing 100% right now. So that's why we are trying to see if, say, dark matter subhalo can explain this. But for the dark matter subhalo, because it's dark, so we don't have any kind of pre-constraint on where the location of the perturber. We just let it to be anywhere, and then see if we can mimic the signature we are seeing here. So that's kind of the other thing we're doing. But basically, the mismatch is just purely caused by the data and the Newtonian we have.
Okay, I see. So it's purely from initial conditions.
Right, initial conditions. And again, the initial condition is sampling from the observations for the current location as Sagittarius. And depending on what the sample for that realization is, this will change dramatically. I probably should show another one, but another one will be no kink at all, no kink at all. It's just smooth. So that is the 95% of the realization we see. So here we are not saying it's caused by Sagittarius. We're just saying there might be a chance that is caused by Sagittarius based on what we know about the current location of Sagittarius.
Okay, so I mean, so in the hypothetical scenario where we have some satellite galaxies we have not discovered yet, So
that's also possible. So in theory, like satellite galaxy is one of the subhalo, right? So currently we are calculating the subhalo, and we are calculating calculate this one. For this one, we are calculating the mass and the orbit. So the mass is something between 10 to the 7, 10 to the 8. I think we are getting something like that. So what I would say is yes. So that could be in principle actual a galaxy, not a really dark thing, right? Because all we calculate is just the mass and the size and the orbit. But yes, it's also possible to be a galaxy that we don't see right now. But the idea for subhalo mass function reconstruction is to get the mass as a function of the number as a function of mass. So it doesn't really matter if it's a true, like it's a visible galaxy or invisible dark matter subhalo. At the end, what we want to use this technique is to do this mass function. Well, but I would say it takes probably another decade or two to get there.
Yeah, thanks a lot.
Okay, so any additional questions or comments for Ting today? Okay, I think I didn't see more hands up. Okay, so if not, let's thank Ting again. And this is our last seminar talk in the spring schedule. We will resume the N3AS seminar talk for the summer schedule in June. So please stay tuned. Thank you.
Thanks very much for coming.
Thank you, Ting.
Thank you. Bye-bye.
Bye.
Thank you.
Bye.